Hey guys, Uma here and welcome to another one. In today's video, we're going to be going through Leetcode problem number 64, minimum path sum. Let's jump into it. As I've said in all of my previous videos, the first step to solving any programming problem, Leetcode or wherever, is to read and understand the problem statement. I've taken a screenshot of the problem statement here from Leetcode and let's jump into it. The problem statement states that given an m by n grid filled with non-negative numbers, find the path from the top left to the bottom right, which minimizes the sum of all numbers given along its path. Note, you can only move either down or right at any given point in time. They also give an example here where the grid goes like this. This is a 2D representation of the grid, but they also have an image here, which is pretty good for us to understand. The output is 7. The explanation, because from the top left, which is here, to the bottom right, which is here, the minimum path goes from 1 to 3 to 1 to 1 to 1. So that's what they basically said here. Now, it is worth understanding what the problem is asking for, right? The input is a grid and the output is 7. Here they give an explanation given the path, but they're just trying to help us understand what the solution is. So now that we've read the question, the first thing we have to think about is, okay, let's just say what's going through our mind. This is one step that a lot of people often forget during programming interviews. Say what is going on in your mind, right? Say your thought process. You're there, you and the interviewer are there to solve the problem together, right? You're gauging how you think. It's not just about you coming up with a solution. They want to hear how you come up with the solution. And I know the proper answer to the question, but when I saw this question the first time, the first thing that came to my mind is a greedy algorithm. A greedy algorithm is an algorithm that takes the best choice, given all the options it has at any given point in an algorithm. So let's give an example. Using a greedy algorithm, it would start from 1, right, which is the top right corner, obviously. Now, from 1, we can either go to 3 or we can go to 1. A greedy algorithm would have chosen 1, right, because we're trying to minimize the sum till we get down here. And if we're trying to minimize, then ideally we should go 1 because 1 is smaller than 3. But right off the gate, that doesn't work because we can see clearly here in our solution that the minimum answer goes through 3. So if at any point in time we're picking the minimum between our two options, right, when we have to go down or when we have to go right, if at any point in time we're choosing the minimum in those two options, then that wouldn't work, right? Quite frankly, clearly, that wouldn't work. So at this step, I would backtrack, right? I tried thinking about the greedy algorithm. It didn't work. Clearly, I stated why it didn't work. I would then backtrack and say, okay, what's one other way that I could use to solve this problem? And quite frankly, brute force, right? As a matter of fact, some people would say you should have thought about the brute force method before even thinking about a greedy algorithm, but I don't think it matters. If you have a proper way or if you have an optimal way to solve a problem before you think about the brute force, then that helps, right? You may have thought about the brute force, but either way, just say your thought process, right? Right now, I'm speaking to you, well, I'm speaking to a camera, but this is how I would talk to an interviewer, right? I'm telling you everything I think. So we tried a greedy algorithm approach to try to solve, the most optimal way. It didn't work. Now I'm going to step back and say, without using any fancy algorithm that I've learned, what is one way I can try to solve this problem? Brute force. So at any point in time, we can either choose to go to the right or we can go down, right? Now that we're at 3, we can either choose to go to the right or we can go down again. From 1, we can choose to go to the right or we can go down. If we draw this out as a tree, it'll look something like this. 1, 1, 3. Well, from 1, we can go to 5 or we can go to 4. So what that would look like would be 5 or 4. From 3, we can go to 1 or we can go to the same 5. So this would come down here like this, and we would have this going to 1. From 1, we can go down, or, well, from 1, we can only go down. So from here, we would go to another 1 here. From 5 here, we can go this way, or we can go this way. So we would have 5 going to this 1 and 5 going to another 2. Now, from 4, we can only go to 2, so we would go this way to 2. From 2, we can only go to 1 here. and from 1 we can only go to 1 here. So this is 2 and the 1 here, then we would come here. This may be a bit hard to understand or visualize, but try to draw it, right? Basically what we did was at any point in time we can go down or we can go right? We can either go down or we can go right. And if we use that to abstract the 2D array, we can come up with a graph like this, which basically means we can then come up with an algorithm, right? Which basically says start from the root here, which is 1. Then pick a path, right? Go down this way. Maybe this way we get to 3. Then from 3, we can either go 2 choices again. And at the end of the day, any path we choose to go down is going to end up at 1. We can then add the sum of all the numbers that we encounter through any of our multiple paths, and it'll eventually come back up to 1. It may be hard to visualize, but this is actually a common recursive problem. So I would suggest you go through it. There's multiple problems that have the same structure. I would suggest you go through it. But that would be the brute force method, right? Start from here. From here, you can either go this way, you can go this way. Well, choose to go this way. From here, you can go this way, you can go this way. Essentially, you're exploring all the paths down through the tree. And when you come back, you find the minimum of the both of them, right? So if the minimum of everything down here through a specific path is smaller than this one, then you will go with this one. Let's take a look at what that algorithm looks like quickly. Let's take a look at the solution for the brute force algorithm. I've pulled it up here. If we look here, at any point in time during the first if statements, if we're at the beginning of the grid, we return the maximum value, right? The next if statement basically states that if we're at the end of the grid, then we return the grid value, right? Which is basically this last point here. Then the final statement says, if at any point in time we're not at the beginning or at the end, we return that value, so of the spot that we're in, then we calculate the minimum between if we go down, if we go right or if we go down. It may be kind of hard to understand until you draw it down, but what would happen here would be, we would start with 1, right? From 1, well, we have 2 options, right? We will return the value of what happens if we go 1, which is here, plus the minimum of if we go down to 1 here or if we go to 3 here, which is basically calculating going down 1 and going down 3. Now, in the recursive function, it'll call itself, right? So what happened is we would now go I plus 1, which is 3, right? 3 would now do the exact same thing and calculate the minimum. So it'll go all the way down, then percolate all the way back up until we return the minimum between the both of them. Okay. This is the brute force algorithm. Obviously, the time complexity of this would be 2 to the m plus n. Why? Simply because at any point in time where we have 2 decisions to make, right? We can either go down or we can go left. And if we draw it the way we did here, in the case of a tree, here we can go this way or we can go this way. Here we can go this way, we can go this way. At any node, we can go 2 ways, right? The maximum we can go is 2 nodes and 2 ways. And the number of nodes are m plus n. That's why it's big O of 2 to the m plus n. This clearly isn't the most optimal way to do it. So let's try to figure out the most optimal way to do it. The proper way to do it is dynamic programming. The thing about dynamic programming that I don't like is a lot of times when you see the solution, they just give the solution right to you, and it may not be intuitive for you to come up with that solution during an interview or something. But I bet you and I guarantee you the only way for you to be comfortable with it is to practice more and more problems. The way of solving this problem using dynamic programming is very similar to the way of solving a bunch of other problems during dynamic programming. And at first, it may be weird to kind of understand or visualize, but once you stick to it and you kind of go with the flow, right? It won't make sense the first time, but then when you continue seeing it, when you see multiple problems and you practice it, the pattern will start to emerge and you see it. So let's take a look at what that would look like right here. I'm going to remove this guy here, and I'm also going to delete this picture here. Clear this here. Okay. Dynamic programming basically breaks down a problem into smaller problems. So let's take a look at what that would look like in the context of this question. Let's say we had a 2D array that's a 2 by 2 array, right? So let's take this sub array here, right here. Let's take this sub array right here. That would look something like this: 5, 1, 2, 1. Let's ask ourselves the same question. What would be the minimum path sum to go from 5, which is the top left corner, to the bottom right corner, knowing that each node we can only go down or right? Well, that will look like this. Well, we can either go from 5 to 1, then from 1 to 2, or we can go from 5 to 2 and then from 2 to 1 here. Either way, let's kind of calculate what would happen from each node, right? So say we have another array here and we have the number 1, right? From 1 here, how can we, from 1 here, what are the number of ways we can get to number 1? Well, we can only come from up here, or we can come from the left here. Those are the only 2 ways we can get to 1, right? So if we come from the left here, right, what would that path be, right? So what would the sum of that path be? Let's think about it this way. If we come from here, right, and we're going this way, the cost of going to 1 from 2 would be 2 plus 1. So it would have 3 here, right? So meaning if we were to come to 1 from this way, we would have to add the cost of where we came from, which is 2. Then 2 plus 1 would be equals to 3. Now, if we were to come from the top here, which is from 1, the cost of doing that would be 1 plus 1, which is 2, right? So now at this point in time, we've broken down the problem into what would happen if we come from either the top here, all the way down here, or here. Now, we've seen that is 2. Now, because we're starting from 5, right? 5 has 2 ways it can come to 1, right? As opposed to 2 that had only 1 way, which was here, and 1 had only 1 way, which is here. Well, 5 has 2 ways. 5 can come from here, then go down here, or it can come from here and go down here, right? So let's think about what that process would look like. If 5 has 2 options, right? At any point in time, it wants to choose the minimum. That's the key part here. The minimum, right? Which minimizes the sum. So what's the minimum between 3 and 2? Well, the minimum between 3 and 2 is 7. Whoa! Wow! So what's the minimum between 3 and 2? The minimum between 3 and 2 is 2. So what would happen is, rather than coming from here and going here, knowing that it will be 5 plus 2, 7 plus 1, 8. So this whole path here would be 8. We would rather go from here, which would be 5 plus 1, 6 plus 1, 7. So we'll choose 7. The second one we chose 7 is that we've already calculated that to get to 1 from here, it'll cost us 2. And to get to 1 from here, it'll cost us 3. Well, our number is constant, right? So we want to choose the minimum between both of them. Well, so it would be 5 plus 2, which is 7. And that's why we came up with 7. So you realize that if we keep doing this, right, at any point in time, we're choosing the minimum between the 2 paths that we have. Well, if we have only 1 path, then we have to choose that path. But if we have 2 paths, then we have to choose the minimum. Let's go ahead and basically redo this whole 2D array in a dynamic programming method. So what would happen would be we would start from 1 here. Now, if we are here, right, and we want to get to 1, we know it'll cost us 3 because 2 plus 1 is 3. So we'd have 3. Similarly, if we're at 4 and we want to get to 1, right, it'll cost us 4 plus 2 plus 1, which is 7. But we've already calculated that from here, right? So we'll just do 4, right? We will do 4 plus whatever it costs 2 to get to 1. I'm going to repeat that again. To get to 1 from 4, all we have to do is say, okay, well, we want to start from 4 plus whatever it costs 2 to get to 1, because that's the only path that we have, which is 4 plus 3, which is 7. Now, we're going to come up here to the next row here, right? Now, let's see. How much does it cost 1 to get to 1 from up here? Well, it only has 1 way it could go, right? It can only go down. So the answer is 2. Now, we'll come back up here and we're at 5 here, right? Now, 5 has 2 options, as we stated earlier, right? You can either choose to go this way, then this way, or you can choose to go this way, then this way. Now, all we have to do is say, okay, what's the minimum between these two paths, right? Between this one and this one. And we've already calculated them as 2 and 3. So 5 would basically choose the minimum between here and here, which is 7. To make sure that's correct, we can again look at it this way: 5 plus 1, 6 plus 1, 7, or 5 plus 2, 7 plus 1, 8, right? So we know that at any point in time from here to get to here, the minimum we can do is 7, because we've already calculated it, broken it down into smaller problems. Now let's go back here. We're now at 1, right? Well, from 1, we want to go to here, right? We can either go this way or go this way, right? So how much does it cost 5 to go to 1? Well, we've already calculated that as 7. How much does it cost 4 to go to 1? It's the same 7. So at this point in time, it really doesn't make sense. Sorry. So at this point in time, it doesn't make any difference, right? So it'll still be 8 regardless. Right? Now, we'll come back up here, right? So how much does it cost 1 to get here? Well, 1 can only go down, right? It can't go to the right anymore. So we'll see how much did it cost this guy to get here. It's 2. So in this case, it'll be plus our value, right? Because we're trying to get here. So how much did it cost you here to get here? Plus whatever I have, which would be 3. Now we're here, right? How much does it cost 3 to get here? Well, for 3 to get here, you can either go this way or you can go this way, right? How much does it cost you to get here? Well, it cost me 3 to get here, plus myself 3, right? Or how much does it cost you to get here? Well, it costs this guy 7 to get here, right? So we're going to pick the minimum between 3 and 7, between here and here, right? 3 and 7 here and here, plus 3. 3 plus 3 would be 6, right? So the minimum between here and here is 7 and here, right? 7 and 3. So we'll pick 3 plus the minimum, which is 3, which would be 6. Now we're here, right? At this point in time, right, as we're here, we can either go this way or we can go this way. And we've calculated how much it'll cost to go from here all the way down to here using all the multiple paths that it has, or from here to go all the way down to here using all the multiple paths that it'll have. Well, we know if we go through here, it'll cost 6. Or we know if we go through here, it'll cost 8. We're picking the minimum at each time. So we'll pick 6 plus 1, that would be 7. And that's it. That's basically the solution of the problem using dynamic programming. So we'll basically have to either we can build it and then we can build this in a new array, or we can build it in the same existing array. There's also another way to do it with one array. You can go ahead and take a look at that method yourself. If you find it more intuitive, that helps, but this method definitely works. Another way to think about this is we're building from the bottom up, right? Back to back SWE made a really cool video explaining that process, right? You can either go from the top down or from the bottom up. In this case, we're going from the bottom up, right? We're starting from here and figuring out, okay, how much will it come from here, similar thing. How much will it come from here, right? Since we've broken it down into smaller problems, we're going down, we're going back up with each step. Again, it may be confusing right now. I guarantee you, when I first saw this thing, it took me a while to get used to it. It took me some time to figure out how do I even come up with this. But the idea is to break down the problem into smaller problem, right? That's why I started with, let's just take this subarray, right? We can either start from here, go up here, right? To go to here, we can only come from here again. So just practice it, visualize it, try to solve more problems that have this type of scenario, right? Dynamic programming, there are multiple problems like this. So that's the way to solve this problem. Let's jump into the code. Okay, now that we're back to the code, this is how it looks. You can use Java or Python, whatever language you're comfortable with solving. I'm going to use Java. So if you remember in our solution, the first thing we need to do is create a two-dimensional array, right? The array that would help us break down the problem into smaller chunks, right? So we do that by basically initializing a new array. So int, I'm going to use the same syntax in the solution just because if you want to go through it, it's basically the exact same thing. So int dp, dynamic programming array, is equals to new int. In Java, you have to initialize the array with the length and the width. So grid of the grid dot length and grid first column the length. Okay. Now that we've initialized the grid, so the new grid, this grid right here, that'll store our solution. The next thing we need to do is start doing a for loop, right? If you remember from the solution that we have here, we started from the bottom right corner. Again, started from the bottom right corner. So whatever iteration we want to do, we want to start from the bottom right corner as well. So we'll go in and we'll start a for loop, right? So for int I is equals to grid dot length minus 1, right? Grid dot length basically gives us the number of rows. Now we want to do grid dot length minus 1 because we are using 0 indexing, right? So we want to start from the last row, right? So there's 0, 1, 2, 3, 0, 1, 2, sorry, right? So there's 3, but we want to start from 2. We want to start from the bottom row, the last row. We would want to go from there. We want to keep going while I is greater than or equals to 0. And we want to reduce I, negative, right? So the next thing we want to do is, so for the last element there, right? The next thing we want to do is we want to get the last column as well. So for int j is equals to grid at 0 dot length minus 1 while j is greater than or equals to 0 as well, j negative. Okay, so the first step that we want to fill, if you remember, the first thing we did while filling out our array was to start from the bottom row, right? We start from the last element, then we want to keep going this way, this way, this way. So let me show that on the screen here. So the first thing we did was we started from the last row, then we went this way to fill, then we went this way to fill, then we went up, then we went this way. So we want to start from here and go this way, right? So the first thing we want to do is we want to check if we are at the bottom row. And the way to do that is we check if if our current row is the last one, right? So how we do that is we do that with a simple if statement. If I is equals to grid dot length, if I is equals to grid dot length minus 1, right? Now, if we're at the last row and we also want to make sure that we are not changing the last element, right? The last element in the grid is right here, right? So we want to make sure we're at the last row, but we're not the last element, meaning that if we're the last row, but j is not equals to the last column as well, because if I and j is equals to the last and last, then that basically means we're at the end here, and we don't want to mess with that number, right? We don't want to change that. So to do that, we would make sure we're at the last row, but we are not at the last column. So if and j is not equals to grid of 0 dot length minus 1. Dot length minus 1. Right. So if this is the case, it means we are somewhere down here, right? If that's the case, it means we're somewhere down here, which means that we simply want to say, if we're here, we want to simply get what is in front of us and add it to our current value to get 3. So if we're at 2, we want to get what is in front of 2, which is 1, and add it to our current value, and we get 3 right here. Then if we're at 4, we want to get what is in front of 4, which is 2, and add it to our current value, which is 3 from our dynamic programming array, and add it to our current value and get 7. So what that would look like would be dynamic programming array of I and j is equals to the grid of I and j. So would be our current grid plus 1 in front of us, right? So it'll be DP, dynamic programming of I and j plus 1. So again, let me try to explain that on the iPad as well. So this is our DP array. Let me just write that down here. This is DP array and this is grid. So what we're doing here is saying at any point in time as we're looping through our grid, if we are at the last row here, then get DP of I and j. So get this item here, get that index and say grid of that item plus 1 in front of it. That's how we break down the problem into smaller ones, right? So that's what that would happen here. Now, the other option is if we're at the last column as well, right? If we're at the last column, we can only get what is directly below us. So we have to write a condition for that as well. So if else, if j is equals to grade 0 the length is 1 and I is not equals to grade the length minus 1, then we simply want to say dp of ij is equals to get whatever is 1 below it. So it's going to be grid of I comma j plus grid of 1 row below. So I plus 1, right? So it starts from 0, 1, 2. So I plus 1 and j. Now we're at the point where we've basically handled the two extreme cases, right? So this row and this row, right? So we basically handled the last row and the last column. Now at any point in time, if it's not the last one, the last column, if we're in the middle, right, we want to basically take the best option between what we will get if we go right, which we've already calculated, and what we'll get if we'll go down, right? So that's basically what we're going to do next, right? So we're going to say else if we're not at the last row, so if j is not equals to grade, I'm just going to copy this here, right? So if we're not at the last column and we are not at the last row, this is the last row, then basically what we want to do is want to say the array that we're creating at I and j is equal to the grid at I and j plus the minimum, right? So math.min of the array of the DP array, so the dynamic programming array of the values, right? So if we're here, again, back to the iPad, if we're here, right, we want to take the minimum, if we're trying to calculate the value for here, we want to take the minimum between here and here. And to get here, we're basically going to add the column by 1. And to get here, we're basically going to add the row by 1. So we would say dynamic programming of I plus 1 j and dynamic programming of j plus 1 I. Let me just make sure to look to make sure this is correct. Yes. And then finally, if what's happening is, and then finally what would happen would be, so we're not, we basically have the first case here stating that if we are at the last row, but we're not at the last column, and if we're at the last column and we're not at the last row. So this is basically helping us not to change the value here, right, in a new dynamic programming array. So essentially what we've done here is we've tried to fill in every value for our dynamic programming array except where we're the last row and the last column. So if we're at that place, then we simply want to get the if we're the last row and the last column, which is basically our destination. We want to get the value of the destination and input it into our dynamic programming array. So what that would look like is we would simply say, well, the last case would be I, j is equals to grid of I and j. Yeah, that's pretty much it. Then finally, if you remember from our array here, the answer would be the final value, right? The answer would be grid of 0, 0, right? So we simply return dynamic programming of 0, dynamic programming array of 0, 0. And this should be it. We can go through it again one more time, right? We're filling in a new array that should have the results, right? That basically has the smaller problem broken down into the bigger problem. We're basically filling in a new array that has the bigger problem broken down into smaller chunks. So what that would look like would be start from the beginning. If we're at the last row and not the last column, then basically take one in front and add to it. And if we're at the last column but not the last row, then basically just take one from the bottom and add to it. Otherwise, take the minimum between the 2 points of if you go down or if you go right. Otherwise, just take the value. And this would actually be the first case, right? Because we're at the point where I is equals to the last one and j is equals to the last one. So it'll actually fill in the last value, which is zeros, which is the bottom right case first, and then it'll then build it backwards. So let's run this and see what that would look like. Okay, syntax errors. Pardon me, I'm used to programming in Python, and Python doesn't really care about colons. It's been a while since I've done this in Java. So there seems to be a problem with our logic. Let's basically try to debug it. So I figured out what the original problem was. I made a mistake here. It should be dynamic programming of I plus 1j and j and I and j plus 1. The first index is always the row, but I made a mistake and swapped those two. And I tried it and I got another error here. It's still not giving us the right answer. So I'm gonna take a while and debug it again, and let's see. So this is another reason why you should go through your code again. I found a problem. So when we're creating a new DP array, we want to initialize the value of the DP array with the grade value and the place from our DP array, not the grid again. So this should say dynamic programming array of 1. So if we are the last column and we're not at the last row, we simply want to get the value from below the dynamic programming array and add it to our current value to get the new one. And so that should currently work, and that works. If we submit it, that basically works. So yeah, that's basically the problem. It's a tricky one. It also, I think Leetcode also says it's a medium problem, which I can understand why. It's a classic dynamic programming problem, and the only way you can get better problems like this is to solve them. They may not come intuitively. So what I'm saying is it may not be easy for you to recognize them at first, but once you basically keep solving them, you basically see a pattern in the problem, and it automatically becomes intuitive. Thanks for watching, and catch you on the next one.